You can go ahead, Michael.
Okay, welcome everyone to the Quantum Photonics session. I am Michael Reimer and I'll be chairing this session. I'm from the Institute for Quantum Computing in the Electrical and Computer Engineering Department at the University of Waterloo. And it's my pleasure to introduce the first speaker from INRS in Quebec. It is Roberto Morandati. Can you please share your screen?
Let's hope that everything is working. You tell me, share.
And he will be talking about integrated and fiber-based components for affordable and scalable quantum technologies. Okay, go ahead. Thank you.
Okay, thank you, Michael. I hope you can hear me. It's okay, you can see the screen. Yes. So I'm going to talk about some of the recent work we actually did. And of course, you have already heard about the title from Michael. And I would like to say before starting that actually this is not only my work, but is also the work of many excellent students and postdoc. Here you have some of them, and quite a few collaborators around the world. So we know that quantum physics has been, let's say, around for many years, but the broad technological potential has only begun to be explored now recently. And in particularly, I mean, when we think about quantum mechanics, we hear those days that the famous word quantum 2.0. In fact, quantum 1.0 actually is a technology that is around for many years and actually deal with laser systems, magnetic resonance image scanners, for example, transistors, and nuclear power generation. More recently, there has been quite significant technological developments and people starting to look in the improvement in control quantum systems. And that's what we lead us to talk about quantum 2.0. And in particular, we think about that for computing and simulation, for communication security, and for sensing and timing. So there are an host of new application that is coming to life more recently. So of course, there are many kind of platforms that can be used to perform quantum operation, of course, solid state, you name it. But one of the key one, for many reasons, is photonics. And both in terms of historical investigation and also contemporary technology. So what are the advantages of using photons? Well, they have low coherence. So basically they can interact, they can propagate without interacting too much with the surrounding environments, so without losing their quantum properties. They can create accessible way to perform state entanglement. And basically they are compatible with the present fiber, mostly the present fiber telecommunication industry, as well as the silicon chip technology. So when we talk about CMOS technology, we can import many of those already established technologies to the world of quantum optics. And last but not least, photons can be used in numerous degrees of freedom. So in terms of degrees of freedom, we can think about the early work in which the information is encoded in either position or path. We can think about the polarization, so we can decide which quantum state, depending if the polarization is vertically or horizontal, and these are very well known. But more recently, there are less intuitive degrees of freedom that came to life. So for example, one is the arrival time. If you have a discrete, time, let's say pulses or whatever, or it can be the frequency if we can have the state encoded in different colors. And those relatively new degrees of freedom actually are very friendly for telecommunication system, because in telecommunication system, we cannot really often control the polarization, while for position and path, we need difficult control mechanism. So these are just two examples of not so recent anymore, previous work we did. One is about the use of time-bin entanglement. Time-bin entanglement to do a complex quantum state based on the temporal degree of freedom, and that the other one is a word that is a little bit more recent about the possibility to create high-dimensional photostates on a chip using, again, this discrete formalism. One of the problems that we face when we develop quantum photonics is actually the lack of accessible and scalable tools. So if you take an experiment that you do in this domain, maybe it will take 3 years just to prepare some customized equipment that you use in your experiment. Then maybe another year or so will be taken by try to interface this equipment, and then only the last year of the project is the actual data collection. And of course, this is not really what we want, but we would like to have systems which are mass producible and have low footprint and expensive, also energetically wise, we can say, that are compatible with the very mature infrastructure that we already have for the telecom system, and that leverage the established degrees of freedom, which I mentioned before. So in terms of scalability, we would like to have, for example, the possibility to use off-the-shelf telecom components. So what kind of process we need to take care of? First, we need to do the quantum signal preparation. Then we need to propagate through the channel and maybe do some signal processing. And finally, we need to characterize the signal that include the non-classical information. So the kind of degree of freedom that you can use is the frequency degree of freedom, the time degree of freedom, and maybe the combination of the two. So in terms of frequency, we can create source. By the way, we don't use deterministic sources, but we use typically sources that are based on spontaneous four-way mixing. And then we have technologies that try to simplify this source by, for example, using pump source hybridization. Again, we want to do all the processing through using off-the-shelf telecom components, as I told you, and then, we would like to be able to acquire the single photon spectrum to process it. If you look at the time degree of freedom, we need to introduce new kind of components like very high precision interferometer, and then we can do the detection by using RF controlled quantum interference. And then, we can combine the 2 degrees of freedom to create upper entangled state, of course, again, discrete domain, to perform coherent control of frequency time states. And when the states become very complex, actually, we cannot really characterize it anymore by using tomography. So we need to think about a more clever way to characterize those states, and maybe working with theoreticians to create good entangled witnesses for the state. And I'm going to talk about more the technological side. So our work about the pump source hybridization, the interferometer, and how we did the coherent control of frequency time states. So let's start with the source. What we typically use is a microring resonator, which is a very, very small cavity. So basically, we create a set of resonances which have a large free spread range. We are talking about value that goes between 50 gigahertz and 200 gigahertz. So they're nice value because you can process them by using standard electronics. Then what we do, we take a pump, maybe we enter with 2 photons, which if are equal, they correspond to the degenerate case. And then by using spontaneous four-way mixing, we can create signal and idler. You see the one with the same colors are let's say, generated at the same time. And in order to do that, you see we need to have momentum and energy conservation, which is actually phase matching, and then leads to these photons, which you can see are generated symmetrically with respect to the pump. So here there is some work actually ongoing on this kind of technology. This is our work, but there are many other groups, like the group of Baioni, the group of Andy Weiner working on the same thing. This is another work that we did using perpendicularly polarized state. We look at the multi-photon states. We look at high-dimensional state. Also, that work was also done by the group of Weiner, as I mentioned before. And then, other people are looking to quantum comps from second-order media. I forgot to say we use glass, so it's a third-order media. Second-order media have the advantage that they're typically more nonlinear, so you need less energy to generate this kind of phenomena, but at the same time, it's more difficult to do phase matching. So one of the main difficulties that we face is to feed the microcavity. So typically people use external sources to do that, which is not ideal because, of course, you're going to affect scalability. There is added complexity. There is a lack of energy efficiency. And there is also a lack of output versatility. So there are a lot of problems to be solved in this respect. So we propose an alternative scheme in which the microring resonator is nexted inside the longer external cavity. So we don't need any external pump, which is replaced by an amplifier. So what's happened here, I apologize for the beginning, I don't know what's happening here, but soon it should become better. Anyway, we have the pulse that enter the microring resonator. Then we can generate a pair of photons, signal and idler, and then we can output it. And in the meantime, the pulse continue to go to the cavity, and then the process is repeated. And here we can see a signal generator and an amplitude modulator that allows us to carve the pulse inside the cavity if you want to do some signal processing on control. So in the nested cavity configuration, we have actually two cavities. One is the microcavity, which has a large free spectral range, and one is the microring resonator that has a large free spectral range, and that one is the long external cavity. Being long, the free spectral range is much smaller. So if you look at one of the resonance of the microring resonator, you will see all the modes coming from the long cavity oscillating inside. And typically these modes are not are oscillating independently, and that actually gives sort of we can say intermittent of chaotic behavior. However, we can use, for example, an active process like with an RF modulator to lock this phase together. And then when you have mode lock, you have a nice train of pulses. And that is the kind of, let's say, measurement that we get out of it. One thing that you can do that is very nice, actually, you can use your RF to change the free spectral range, to just cut some frequencies. And then it allows you to do what we call harmonic mode locking. So we can adjust the repetition rate. And this is very useful for a couple of very good reasons. So if you keep the power, if you want to have enough events that you generate, typically you need to increase the power. But then if you increase the power, what is going to happen is that you can have stimulated effect. So it's going to affect the quality of your correlated photons. In order to increase the detection rate, what we can do is actually, as I show you here, increase the excitation repetition rate by using, for example, harmonic mode locking. And then we can see that the coincidence to coincidence ratio, which is the quantum equivalent of the signal to noise ratio, stay constant. And also we can still work with a nice single modes. So this kind of thing is schematic is very promising, and we are still working on that. Then if you want to do some serious operation in a time domain, we need to develop an interferometer that works as we wish. And by the way, these interferometers are very fascinating machines. I mean, they're very easy to explain. So basically you have two arms, and by changing the length of the arms, you split the signals in two, and there is interference. And of course, ideally, you go from 1 to 0 in this kind of periodical behavior. But of course, because of real life constraints, you have background noise, you have phase drift and instability, you have losses, so things are not so perfect. We all know how important are interferometer. We can just think about the LIGO interferometer and all the kind of very complex technology that there is behind, like here in this case, we have internal seismic isolation. But of course, we cannot really go that way. And we need to find something that is affordable and still very precise. So if you take the typical kind of interferometer, you have this function, but there are a few problems correlated to that. One problem is that basically for one values of intensity, you have two values of phase, so you have ambiguity. And second, the variation here is much slower, for example, than the variation here. So the stability is very phase dependent. So my student actually came with a very bright idea. So they came with the idea to create a second reference signal that is just shifted by pi2, and because of that, you have both the signal in phase and in quadrature, and then you can reconstruct unambiguously the phase itself. And in order to do that, I'm not going too much in detail, but what they do, they take a beam splitter, then they have acoustic optical modulator that really shifts slightly the frequency. So you can then adjust it to have a pi phase shift, and then you can, a pi divided 2 phase shift, and then you can use a polarized beam splitter to create two perpendicular polarization. This is very nice because being the frequencies so near, it's very difficult to separate them with a filter, but it's very easy to do with the polarizer. Okay, so we have very stable kind of device. I think, let's see if I can show you the movie. So here is how it works. If there is no stabilization, it's enough that you breath and everything, it's oscillating like crazy. But when you put the stabilization mechanism, then you will see that the system becomes absolutely robust to any kind of perturbation. You can knock on it and nothing change. Maybe you will have phase shift that are always of 2 pi value or multiple of that. So that is something that basically we did to perform our experiment. So it's work also with attenuated reference to reduce the background. We can still get very nice results by increasing the integration time. Here, there are 3 experiments. You see, longer the integration time, better it is. We can even use a pulse reference if you want to have less the minimal background counts. And here are some measurements taken with a fast photodiode. And we can even play and interleave the pulses and then do the characterization of the correlated photon as well as of the 2 signal, the 2 references by using the same single photon detector. Actually, this is a bit more long time, but it's something that can be done, as you can see in this experiment that was done recently. The paper came out this year. So now that we have this object, we can do the coherent control of frequency time states. And I will be very brief. For example, we can carve 3 pulses and create 3-time beam. So here is the way that the information is brought in the temporal domain. And I'm not going too much in detail. This is the state where you have the 3 times beam. I will show you an experiment that we did to create 2-time beams. So you have this unbalanced interferometer. So you create those 2 pulses. And basically, you can create several frequencies through spontaneous 4-way mixing. And then you multiplex them. And you can characterize them by using other 2 identical unbalanced detector, but with a different change of phase. You can do typical measurement, which is quantum interference and tomography. Or you can use the fact that you have many lines in the cavity, so many pairs of signal annihilator. So you look at the frequency domain instead, and you think about these photons as a superposition of different frequencies, like in this case. And then, the setup is slightly different. In the beginning is the same. You have your pulse laser that creates states through spontaneous 4-way mixing. You will create your comb. But now what we do, we replace basically the unbalanced interferometer with a wave shaper. So we are able to equalize the lines in the comb to adjust carefully the phase, and then to perform again the same kind of measurement. We will use now, after the first shaping, a phase modulator to create the coherent mixing required to make these photons, this frequency indistinguishable. And then, of course, we do the same characterization by using another wave shaper. We can still look at quantum interference, tomography, and so forth. So we can combine these 2 degrees of freedom, like we did that in signal and time. So we can do basically hyperentangled state, which are product states. And we can even dream to do cluster state. But in order to do cluster state, which are very useful for one-way quantum computer, you need to change the phase of these 3 frequency beam that are associated to 1-time beam in a different way for each one of them. And you can see it's very challenging. So my student came out with this idea. So we have this state. We work with Raman Kashyap from École Polytechnique to create a series of fiber-Bagretti mirrors. Different frequencies are reflected at different time. So basically we separate all this frequency being in the time domain, and then we can process them independently with an amplitude modulator and a phase modulator. And then we can use a circulator to go on the other side and recombine the signal. And basically we can create our class state in which the phase is controlled individually. So I think I'm almost on time to finish, maybe 1 minute late. So basically we did a new class of compact pulse photon sources, a pair of photons. We look at low complexity phase activity scheme, and then we use coherent control to control the individual terms of the photons composing the states. And basically this work has been followed up by other works. The group of Pan used the exact scheme of our interferometer a couple of years after we patented it. The same attenuation scheme was used in this experiment. People are now scaling up the kind of work we did in the frequency domain, and we very importantly, my student, I'm not involved, founded a startup that is called QD2022 Photonics, and it's get funded by the Arrow, by the SPY and Centec, the Creative Destructive Lab, and hopefully they will be successful. So future target, quantum source with passive laser, maybe improve them, pulse-to-pulse coherence in compact pumps, so increase the performances, and reference interferometer for atomic standards. So that is the few idea for the future. And this actually, I think I'm just finished my talk, and thank you very much.
Thank you very much, Roberto, for the very nice talk. We have time for some questions. You can post them in the Q&A on the WOWA app, and I can read them out. And
maybe you read them out, because I still don't understand very well this app. I download it, but I'm a bit not very technological. I'm going to open it. But if you see any question, maybe it's better you ask me directly.
Yeah, you can also try that, since I don't see any on the app.
There is a new no. Later, there is one new question asked. No.
That's me, just saying you can post it here.
Okay.
So maybe if someone has a question, they can just say it.
Too much technology with this WOWA stuff.
Mikhail.
Yes, I have a question. So for the nested cavities at the beginning, how do you get the pulses started? Because there isn't like a, is it just with the modulator? Because there's just the amplifier in the big loop and then the small cavity.
Yeah, actually we can start it with the modulator, and this is a very actually is a very actual topic of research. So one of the problem of this nested cavity thing is stability. So you need to have active feedback. Typically, if you think about these laser systems, now we are below threshold, but even above threshold, they tend not to be in what we call attractor state. So once you start them, they don't tend to stay in the right state for a long time. So you need to control everything by using a feedback mechanism, by using Peltier, and by, again, as we say, using the RF modulator if you want to lock them. But it's not easy. So they don't tend to stay naturally stable. You're right on that.
So I have a question for the entangled photons you make with the 4-wave mixing. How far are the signal and idler away from the pump? And how many?
That's a very good question. So typically we manage without difficulties to go as a dimension of 10 by 10. So we can use up to 10 lines. That's because if you go far away, you tend to start to have many kind of effects. You start to have Raman, and you have maybe dispersion. You start to have effect that you need to control. So if you want to, that's need to the next question that I'm sure you're thinking about, which is how scalable is the system. And in order to make it more scalable, you need to play other kind of tricks. So typically you will need a microring resonator that are very high properties, but lower free spectral range, which means that you will need to have longer cavity, of course, like I said before, but then you need to control the losses better. So either you should go down to 25 gigahertz free spectral range, and you are still able to process everything with electronics. And of course, it will be nice to have modulators which have a large bandwidth, operational bandwidth. But of course, we are going at the edge of the technological challenges. So this is a very good point, and it's not so trivial to solve for the reason I told you.
Okay, thank you very much. And in view of time, let's thank Roberto again for the very nice talk.
Thank you to all of you.
You're welcome. And now we can go to the next speaker, is Mikhail Bashti from the Institute for Quantum Computing and the Electrical and Computer Engineering Department from the University of Waterloo. And he's going to be talking to us about manipulating single photons with atomic ensembles and tracking old challenges using nanophotonics. Go ahead, Mikhail.
Right. It looks like it's working. So yes. Thank you very much for the invitation. It's a great pleasure to be speaking here, and good afternoon to everybody who has joined this talk. So today I'll be talking about two somewhat niche platforms for quantum optics with atomic ensembles. So they are not completely brand new, but they are also not what you would call mainstream, or at least the uses that we are trying to explore with them are perhaps still waiting for their moment. So the one of the platform is atoms inside the hollow core waveguides. And the main benefit of this platform is that you can achieve sort of optical medium of large optical depth. And this medium consists of identical quantum emitters. So this is something that it's kind of hard to get with solid state emitters, but atoms, since they sort of a host medium is vacuum, you sort of get these like identical quantum emitters, and you can sort of start looking at some ensemble effects. The other benefit that you get is a very tight confinement, or fairly tight confinement over long distances for the photons that interact with the medium. So now the photons propagate in a waveguide, so they stay focused for sort of as long as your waveguide is, to sort of sizes at sort of the micrometer or tens of micrometer scale. The other platform that I'll be talking about is mirrors based on photonic crystal slabs, which are there are a few examples of those shown in the picture. And the main benefit why we are exploring these is these sort of somewhat exotic mirrors can be used to create cavities inside hollow core waveguides in a way that you can still fill the hollow core waveguide with gas because the photonic crystal slab has holes in it, so you can pass atoms or molecules through the holes and fill up your hollow core fiber. And these mirrors are also interesting because they can be designed to be dichroic for either polarization or wavelength. So you can now create new types of cavities that are not possible with conventional metallic or Bragg mirrors. So I'm going to talk about which problems we are trying to solve with these problems and how we are doing on that. So problem one, that sort of some people might be asking, is it possible for for photons emitted by quantum dots to interact strongly with atoms or atomic ensembles? And here, sort of the advantage of atoms, or in particular laser-cooled atoms, is that they can give you very long coherence times, which is good for sort of quantum optics processes and photon storage in particular. And there's also potential to achieve very strong optical nonlinearities with low power light with laser-cooled atoms. However, the downside is that conventionally people would use atoms or atomic ensembles to deal with pulses with bandwidth sort of up to tens of megahertz. So people sort of usually assume that atoms cannot handle very fast pulses, and oftentimes they can't, just because of their sort of natural line width is rather narrow. The other, the quantum dot that we are playing with, and this is in collaboration with Michael Reimer's group, also at the University of Waterloo, is a quantum dot in a semiconductor nanowire, which offers a high brightness source of single photons and also entangled photon pairs. And because the quantum dot is sitting in a waveguide, it can be relatively well coupled into single mode fibers. However, there is a bit of a mismatch between this quantum dot and atoms, because the photons emitted from the quantum dot have bandwidth of at the order of a gigahertz, which of course presents a bit of a challenge, even though this is one of the sort of better quantum dots in terms of its line width. So have people tried sort of sending photons from quantum dots into atomic ensembles? And the answer is yes, they have. But sort of all of these experiments, which have been done over sort of the past decade, demonstrate in particular sort of a group delays or slow light with sort of photons emitted by quantum dot passing through a vapor cell with rubidium gas or other rubidium or cesium gas. And what this is based on is if you sort of think about the sort of the refractive index of a two-level system, you can get so this was actually demonstrated relatively recently, given how simple this is in our 2007. If you approach the resonance of a two-level system, you get a slight slope in the refractive index, which translates in sort of a reduced group velocity. So you can get group velocities kind of at the order of C over 10 or sometimes even C over 100. So this was first demonstrated by Howell and Boyd in the 2007. But what it gives you these relatively large gigahertz size windows near the resonances of say alkali vapors. So this has been sort of tried on with single photons. So the single photons were produced. So the original experiment was done with laser pulses, but now later on several groups kind of tried it by sending single photons from a quantum dot through a rubidium or cesium cell and sort of registering sort of a interesting group delays. However, this would be kind of considered a weak interaction. You sort of are not really doing much to the photon, and we would like to do something more interesting. But what happens in this case, or for the case of room temperature and free space atomic clouds, is that your interaction is limited by the optical depths that are available from these ensembles. So here I would like to point your attention to the, again, somewhat newish technology of hollow core optical waveguides. They come in various flavors. The main two classes are hollow core optical fibers and then on-chip hollow waveguides, in particular pioneered by the Schmidt group at the University of California, Santa Cruz, and the Corby group at University of Alberta. And what's kind of strange about them is they allow guiding of light in low index region, which now you can leave empty, which means you can load it with atoms. And this has been a relatively popular topic to explore. There is a bit of a community sort of established around these experiments. So there are sort of quite a few groups who play with hot atoms loading into these waveguides. And there is another about half a dozen to maybe a dozen groups that sort of have tried it with cold atoms. And of particular interest was this, for us, was this experiment from the Walmsley group from a few years ago, where they demonstrated the storage of sort of sub-nanosecond laser pulses in a hollow core fiber filled with rubidium vapor. And because they have a sort of managed to fill it pretty well, they were able to achieve optical depths of about 1800. So just to define an optical depth means how much your light gets attenuated when it propagates through a medium. So it's basically the optical depth is the e to the minus OD is the transmission of light through your medium. And it's usually used as a sort of or it serves as a figure of merit for these interactions between atoms and optical pulses. So this was good news, but of course the sort of the storage time in these memories is limited by the transit time of the atom through this sort of 20 micron diameter core, and sort of because the atoms are moving, once they hit the wall, they forget if they were storing any photons. So this was kind of a limitation. So here we are kind of aiming to do this with laser cooled atoms. And here the good news that it is possible to load optical depths into a hollow core fiber with cold atoms that are sort of at the order of 10 to the 3, hopefully at some point 10 to the 4. And this has been sort of demonstrated by the group from Darmstadt a few years ago, where they were able to demonstrate an optical depth of 1000. And now, as we saw in the previous slide, once you go to these high optical depths, you can start playing with very short pulses. So this restriction of 10 megahertz bandwidth goes away. Now, the other problem that I wanted to sort of focus your attention on is the interaction between, if you're trying to achieve sort of nonlinear optical processes, which you can think of as interaction between two photons. And now the idealized picture for this would be sending two photons through a cloud of atoms, and as the photons pass by each atom kind of mediates a little bit of interaction between the two photons. So by the end, the photon pass through the atomic ensemble, you get sort of some sort of exchange, so the photons talk to each other, and the longer the optical, the longer the ensemble, the more interaction there is. However, in reality, what oftentimes happens is that the two photons have non-matched group velocities, and once the two photons do not overlap, sort of any extra optical depth doesn't help you. So you kind of have to figure out how to solve this problem of sort of a limited optical depth, or sort of the mismatching group velocities. And one way to do that is that you send one of your photons through an ensemble, and then you try to match the group velocity by adding a cavity. This is kind of like a very high level explanation how this is done. And there have been sort of some very nice experiments done in this direction by the Volatil group at MIT, where they were able to sort of demonstrate an interaction between two photons kind of in this kind of hybrid system, sort of half atomic ensemble, half cavity enhanced interaction. However, the challenge there is that the sort of one of the photons in this case is very well aligned with the ensemble, so it interacts with the ensemble very well, the one that's kind of aligned with the sort of elongated axis of the ensemble. But in their experiment, the second photon was sort of not so well aligned with the ensemble. So what we are hoping to achieve is create a system where both of your photons are well aligned with the atomic ensemble. So most of you probably know multi-layer Bragg mirrors, which can achieve very high reflectivity. However, it's relatively hard to make them wavelength selective. So what we would like to achieve is to make a mirror that's highly reflective for one polarization or frequency and transparent to the other one. So this would allow you to sort of do these alignments sketched in the picture on the right. And here, our proposed solution is to use mirrors based on photonic crystal slabs, which allow you sort of more control over sort of what wavelengths can go through and which ones will be reflected. So just very quickly, I'll try to talk about the sort of the atoms inside the hollow core waveguide and the experiments we are doing with that. So what we do here, we start with a sort of a conventional magneto-optical trap, which is the standard workhorse of atom cooling. We create a cloud of atoms with about 100 million atoms at 20 microkelvin, and then we just drop it onto the face of this hollow core fiber. And we also couple what is essentially an optical tweezer into the fiber, so you get a bit of a potential that pulls in the atoms into the core. So it is not a very efficient process, but it's relatively simple. And the atoms are sucked into the core, and now you can interact with them. So if we sort of look at how the sort of the absorption of our probe going through the fiber changes with time, you see this probe being absorbed in the atoms above the fiber, and then at some point, once the atoms approach the fiber phase, you see this shooting up of the absorption. So this is kind of a proof that your atoms are sitting in the fiber, and then we can sort of scan our probe laser across, say, a sort of a two-level resonance of the atoms, and depending on our loading efficiency, we can see optical depths that range from unity for us up to about 100, but we haven't tried any sort of very fancy loading scheme, so we still hope to push it up by a factor of 1 or 2. But the interesting point is that 200 atoms in our waveguide give you an optical depth of approximately 1. So now I move on to the quantum dot-based experiment. So my lab started mainly as a sort of an AMO lab. So now we are trying to create a quantum dot setup in an AMO lab. So as I said, this is a collaboration with Michael Reimer, but unfortunately his lab is on the other side of the campus, and neither of us were willing to move. So we had to sort of recreate some of his quantum dot setup in my lab. So we ended up borrowing a cryostat, building a high resolution spectrometer, and sort of hacking a picosecond pulsed laser. So these are all sort of standard equipment that you would find in a quantum dot lab, but less so in a sort of atom cooling lab. And also a big shout out to Philip Poole and Dan Dalaku from NRC, who are the ones who grow these very nice quantum dots in the nanowires. All right, so we built a sort of a high resolution spectrometer, and the interesting hack there is that we sort of upcycled a small spectrometer that I bought from eBay to this high resolution system. And we also discovered that if you use an astronomy camera, it actually, because of its sensitivity, it works pretty well as a sort of a high sensitivity camera for quantum optics experiment. And as a sort of a side note, you can also get use this sort of wavelength meter that MOGLAB makes to characterize extended cavity diode lasers as a pretty good resolution spectrometer. And then to get a sort of a picosecond laser pulse source, we use a sort of a fast fiber integrated electro-optics modulator that we stabilize, and this allows us to take any sort of continuous wave diode laser, which is tunable, and create tunable pulses at about 100 picosecond long, which essentially replaces a TISAF laser, which costs about $100,000. So here are just some basic data for characterizing the quantum dot, and kind of one of the new results that we got on these experiments is that if we take our quantum dots and we spray them with gas, in this case nitrogen gas, because of the low temperature, you will see essentially the gas will deposit on these nanowires, put some stress on the quantum dot, and you can use this as a tuning mechanism to change the wavelength of the quantum dot to match precisely the transitions of your atoms. So this is kind of a fairly new result. We are trying to sort of finalize some measurement and then hopefully publish soon. All right, so we also kind of looked as a case study if we can use these high optical depth ensembles inside the hollow core fibers to convert wavelength of the 895 nanometer photons emitted by the quantum dots, if we can convert it either to some sort of a telecom wavelength or to sort of 800 nanometer wavelength, which will be the wavelength that's good for sort of a QKD distribution through a satellite link. So depending which level you pick in the cesium, you can go telecom or you can go satellite link. And it seems that we can get about 93% efficiency if we can get the optical depth to about 10,000. And if you look at this kind of overview plot that sort of looks at the conversion efficiency of single photons in various systems, it looks at our sort of system that's marked by this yellowish area is sort of yellow square. It's sort of fairly competitive with other technologies. So this looks promising. We are trying to put it together, and it's a bit challenging because it's sort of two experiments that you are trying to make work at the same time. So I'm going to shift gears a little bit in the remaining time and talk about mirrors based on photonic crystal slabs. So what photonic crystal slabs are, for those of you who haven't encountered them, is you take a dielectric slab, which would give you this sort of ettalon reflection marked by this green dashed line in the plot. But now if you start drilling holes into it, you will see that these funny resonances will appear in the transmission and the reflection. And now by playing with the periodicity of the hole, size of the holes, thickness of the slab, and so on, you can engineer this to be a mirror. So here we have an example of sort of a particular simulation of a mirror where you can get these sort of relatively broad regions of high reflectivity. And where things get interesting, if you now, instead of having just round holes in a sort of a triangular or square lattice, you can start breaking symmetry in the mirror. So one option is that you start making your holes elliptical and also the spacing not being square or triangular. And this allows you to get polarization selective mirror for linear polarization. Even more exciting, once you decide that your individual cell of the photonic crystal doesn't have to be a single hole, but it can be a group of holes, you get even more degrees of freedom. And here we were actually able to demonstrate a polarization selective mirror for circularly polarized light. So it's a mirror that for a range of wavelengths is highly reflective for, say, a right-handed circularly polarized light and highly transmissive for left-handed circularly polarized light. So you can wonder how you can make a cavity out of this. Well, if you take your photonic crystal slab and you attach it to the ends of a hollow core photonic crystal fiber, you get a Fabry-Perot cavity inside of the fiber. So now just very quickly, you make these slabs by e-beam lithography. And then once you make them, you can mount them onto the end of a fiber using this sort of jewelry-like process where you use you use epoxy glue to attach them to your fiber tip. And this is what the whole system looks like under a microscope. So you can see the end of the fiber in your photonic crystal membrane. And then when we tested it in a setup, we actually did see the Lorentzian peaks in the cavity transmission that you would expect from a Fabry-Perot cavity. The cavity finesse wasn't amazing, but we also haven't fully optimized our fabrication process. So we are right now only at mirror reflectivity about 80%, but it should be possible to go to sort of 99%, which other people have done with these photonic crystal slabs. The cavity is monolithic but tunable by changing temperature. And then sort of the last topic that I wanted to talk about a little bit more about this chiral photonic crystals or mirrors that are different, have different reflection for different polarization of light. So here we just kind of did kind of a PR experiment where we made IQC out of sort of different chirality of structure. And you see that depending on how you illuminate the structure, either the background or the letters glow, and with sort of a more precise measurement on a sort of an actual photonic crystal slab, we got a contrast of about 35, the reflectivity of one versus the other circularly polarized light. The interesting thing here is, in general, when people think about these photonic crystals, they assume they have to be infinite, but it turns out that even sort of regions the size of about 10 micrometers already behave as sort of very good photonic crystals. So next stages is we are sort of playing with assembling these cavities, and we're also trying to develop free space dichroid cavities. But here the challenge is that your mirror needs to also provide focusing. But this is kind of a work in progress. So on this note, I would like to conclude my talk, mostly by thanking the various funding agencies that have been generously supporting us, in particular Canada First Research Excellence Fund and TQT. And also big thanks to the people who did most of the work on these projects, in particular Divya and Rubaiyat and Taehyun, who built these experiments, and then Jeremy and Behruz, who were involved in making these sort of fancy mirrors. So with that, if I have any time, I'm open for questions.
Yeah, thank you for the very nice talk. So we have time for questions. Just as a reminder, you can post it in the WOVA app, and then I can read it out. So maybe I have a quick question. So you mentioned the bandwidth of the kind of like the frequency conversion of the single photons. What's the range of bandwidths you can handle?
So that, let's see if I can find. So the bandwidths, again, it's a bit of an optimization process, but you can get to sort of gigahertz should be possible. And again, if you sort of optimize more, but gigahertz should be doable. I guess this is sort of plotted here. It's the efficiency versus line width, sort of line width of the pulses.
Mm-hmm. Okay, and we have a talk from Rami Tennis. He asks about the quantum dot, and he says, does the nitrogen gas tune the emission spectrum?
Yes, it does. So again, it was done in a little bit of a fast way. So what happens? The quantum dots are sitting in a cryostat, so they're at like 4 Kelvin temperature. And now if you spray nitrogen gas, the nitrogen gas is going to deposit on the nanowires. And because the quantum dot is so close to the surface of the nanowire, the stress arising from the mismatch between the lattice of the solidified nitrogen and the lattice of the indium phosphide nanowire, it will kind of squish the quantum dot and move the frequency of the emission.
All right, thank you. And then the next question we have from Adrian, and his question is, he says that in the photonic crystal lab, you demonstrated polarization filtering. So what else can you filter with one?
No, so it's polarization selectivity. So you can design your photonic crystal slab to be transparent for one polarization and highly reflective for a different polarization. So you can have a cavity that you can probe through the mirrors, and when you probe through the mirrors, some light will see it as a cavity, and some light will just see it as a free space ensemble if you have atoms between the two mirrors.
Okay, so in view of time, let's thank Mikkel again. And I would just like to remind the speakers that you can go onto the Whoa app after and answer any questions that were not asked during the talk. And so let me introduce the next speaker. So the next speaker is Stephanie Simmons, and she's an assistant professor from Simon Fraser University, and she's also Chief Quantum Officer at Photonics Inc. And today she's going to be talking to us about silicon color centers.
Thank you. Thank you. I've been so excited for this because there's a lot of stuff happening in this space and maybe not everybody's aware of it. So yeah, I do wear two hats. I'm the Chief Quantum Officer at Photonics, and I'm also a professor at Simon Fraser. And so the presentation today is going to be mainly on the academic outputs. And some of these are about a year old now. So the most up-to-date stuff is currently being written. I'm not going to talk to it today, but the general program that we have is really motivated by the following axioms. We are very technology driven. We're trying to build distributed quantum computing processors because modular quantum processors are where it's all going. And it's going to be the same kind of platform you want for quantum communications. And our axioms for this is that really, if you can get it working with these three axioms, then you're in a good spot. So we've heard many times through the talks this morning that telecom is really where you want to be. We're furthermore of the opinion that you need a long memory, quantum memory to some degree. And if you can get it working in silicon, you win. Now that, these are axioms and people can take different axioms for their own technological development, but the silicon one, it might be maybe not obvious. We certainly know that silicon is the basis for the modern electronics industry and can print billions of transistors with parts per billion kind of success rate or failure rates. So that's very promising when we're talking about large scale quantum technologies to be able to adopt that kind of backbone. It's also, of course, as many of the people who will be listening to this discussion are aware that it's the integrated photonic platform of choice. So if you want to do large scale integrated photonics, silicon has a lot to offer. It doesn't quite hit everything, but it really is, it's basically, I think, the undisputed leader in that space. And the idea is that, of course, you can work with SOI. So standard wafers you put on top, you can guide the light with printed silicon photonics. And the picture we have is you actually want to put your defects, your long-lived quantum defects, if you're going to have memory and you're not going to rely upon the loss of a photon itself, you want to put the defect right into that single mode waveguide or optical component, and then design it right there, rather than have to do evanescent coupling or any of the rest of it. So that's been the motivation that we've been looking at. Now, silicon is also really the quantum host of choice, really. For a few different reasons. From a spin lifetime perspective, it set early records in this area. And the idea is that we can make silicon basically more pure than we can almost any other solid state material. So this is from the Avogadro project where it was so pure, it's the material of choice to redefine the kilogram. So the kilogram is now defined according to a number of silicon-28 atoms. And so the program to make that material had the advantage of actually getting rid of the silicon-29 spins. So it made this kind of spin zero environment, which allowed us to set all kinds of records. So this is a very old slide now, but a lot of these records still show you the kind of trends. We have solid state silicon options here, which are really outperforming. And if you didn't know, these are Canadian numbers, right? Setting records ages ago. Now, for completeness, after this was made, there is some rare earth material that you can get that's beyond that. But basically, that's the trend. And really, if you're going to be working for a computational perspective, you want to be thinking about the number of operations you can do before that lifetime goes. It kind of sets you the bare error rate. And if you want to have good error rates for error correction purposes, you want to be upwards on that graph. But the lifetime itself can matter for communications applications. So that's why we're quite comfortable with working with spins and silicon. That's where I came from. Moving to photonics was a different game. So there were spins that had optical access. It's just very bad optical access. But again, it's by working with silicon, you can get this dramatic improvement in performance, not just from a spin lifetime perspective, but for an optical perspective. So here, some of those spins that were used to set records on that previous graph this is the optical transition for those. And you can see in natural silicon, it was already known as a ridiculously sharp line, well defined as an ensemble. And you move to silicon-28 and you get it so narrow that you can see zero field spin splittings and the rest. So you can see really, really well-defined transitions. So if you're going to have a homogeneous system, right, you're going to scale this thing up and have them as homogeneous as possible. It's really promising to work with silicon, and especially silicon-28. Now, the challenge with phosphorus was that as a great spin, right, really long lifetimes, emits light in the near infrared, not telecom, but near infrared, the quantum efficiency of this thing just wasn't up to it. And I think that might be the reason why there was such little interest in exploring silicon as a platform for color center development. Of course, NVs and even silicon carbide, they've had quite a bit of work, but very relatively less effort has been put into developing color centers in silicon. The other center that would have been known around this time was erbium in silicon. That has a completely different set of challenges with it. It's a very long-lived radiative object. It does have the efficiency, and it is in telecom, but it's like a millisecond emission lifetime. So if you're looking for high rate or high coupling efficiencies, we're trying to look at a few different options. So when I started at SFU, I started taking a look at neighbors to the phosphorus atom to try and deduce what kind of spin photon interfaces could exist, and just kind of bending the axiom around telecom for a minute. We did find them. Selenium was great. It has an internal orbital transition, which gave us a relatively strong mid-infrared transition that you could use as a spin photon interface. And we got, the transmission and absorption, but really the take-home message for the mid-infrared effort was that gorgeous spin, but it's mid-infrared. It just became it became evident that really we wanted to go take a look at telecom, and the efficiency on these things. Well, no, it wasn't 0.01%, it was closer to like 1%. So we really wanted to push on. And so this opens up a whole, one of the nice things about when you go exploring scientifically is you open up a whole world of stuff. And so what we found is this forgotten body of literature from the 70s and 80s on the so-called radiation damage centers, because of course silicon has been studied to death, and there's piles of color centers. They just went by a different name. So really these damage centers is what you would characterize them as, and what they would do is they would damage silicon and see what kind of luminescence features would prop up. And these are all kinds of structures. They're native to silicon, whereas erbium you could kind of put into anything. As a native to silicon, these kinds of structures, and we began to take a look. So the first set we looked at a couple of years ago now resulted in these are the kind of centers that could be readily created with the natural impurities within our silicon-28 ensembles. And we take a look at them. So there's a full characterization paper for the C center, the G center, and the W center. And that naming convention, again, comes from the 70s and the 80s, where it was clear that they just kind of threw everything and they just labeled them a quart of alphabet soup. So they're interesting because they're right in the telecom regime, and they're really easy to make, super easy to make. The G center is almost impossible to get rid of once you go down that track. Now, to jump to the conclusion, these centers don't have an unpaired ground state electron spin. So there's no direct electron spin to photon interface here, but there might be some indirect ones that I know that a number of groups are trying to look for. But what we did is we took a look at the next one. Oh, we're frozen here. Forgive me. Okay. So the T center, and that's the basis for the rest of this talk. So the T center was one that we unearthed from the literature. It wasn't agreed upon in the literature if it did have an unpaired electron spin in the ground state, but we found that it does, which is great. It also goes through this dramatic optical performance improvement when you go to silicon-28, and it has a fairly good sideband fraction. So why 1326? This is one of a few centers, the T, I, and the M, the TIM centers, as well as a few others, all actually have this unpaired electron ground state spin. You can use, some of them are in the different parts of the telecom band. What we're interested in the T center is the 1310 bandwidth. So this is the O band, like right core in the O band. That is the infrastructure that's used within data centers as single mode fiber to move information around. And also it's the single point, the 1326 is really close to the zero dispersion point of those dominant single mode fibers. So the structure, I'm going to kind of go through it quick because these are short talks, right? But I'll just kind of give you a flavor for what this object is and why we're so excited about it. So it has this 1326 transition. It's an excitonic excited state, so it's temporary, it will emit. The excited state is TX0 and TX1, those both are doublets. And they're split by almost 2 MeV, which means if you're around 2 Kelvin, you don't need to worry about thermal activation to that next excited state level. And so you could treat this as a spin half manifold from an electron spin perspective. The lifetime of this thing is only about a microsecond, which is kind of a Goldilocks zone for what we're interested in, because if you want to put these things into cavities or work in the high Purcell regime, you're going to be taking that lifetime down to nanoseconds or so. And so this is kind of a comfortable starting point where it's not so dim that you're having trouble hunting for individuals, which I'll get to towards the back end of this conversation. In terms of the spin structure, it gets a little messy because there's a lot of orientations. So one of the what you get is you get all these extra nuclear spins that you can play with reliably every single time you make this center, if you're implanting carbon-13 in particular. But that does mean is that like that additional structure has the cost of having different orientations. And so if you're on an off-axis degeneracy, when you're applying a magnetic field, you can see up to 12 different orientations in PL, and actually that's 24 different orientations under inversion symmetry there. So you have quite a bit of space there. But each of them are resolvable through, there's an anisotropic excited state splitting. So you could pick them all out, talk to each of them, and you have a direct access to the spin transitions. So yeah, so the spins, you'll have a nuclear spin and an electron spin. And if you apply the carbon-13s, you would have the ability to have more nuclear spins at your disposal. So while having that spin access, and as an ensemble, we went and took a look at it, and in our first go, initialized the electron and the nuclear spins and showed that they have the expected kind of performance you would get for a simple Hahn echo of the electron and the nuclear spin. Again, T1s so long that you don't bother measuring them, and T2s definitely limited by our home built magnet system, which could be in principle dynamically decoupled away, and which was what gave rise to those astonishing 3-hour coherence times in phosphorus. So we're not worried about the spin performance. We're quite happy with it. It's getting excited about the optical performance, which allows for the networking of lots of these different spins together in a scaled up fashion. So this work, this initial work here is a big PRX quantum paper. Go take a look. It's a beast of a paper that kind of goes through a lot of basic science on the spectroscopy of this. When we walked into that program, we had no real core knowledge about the structure beyond its wavelength and its atomic composition. So silicon and hydrogen and carbon and the unpaired electron spin in the ground state. And then once we were done, we're happy enough with the basic parameters of the center to move forward for integration testing. And so I don't have a lot of time to get into a lot of the integration testing that we did, but there was quite a bit of material development that we did to get this to work into conventional SOI. So what we did is we did a lot of implantation and processing development and took a look at the characteristic spectral diffusion of these centers to make sure that they could perform the kind of optical interconnect purpose that we wanted to do. And that's going to be an ongoing thing, but there was a paper that you could go take a look at where we saw that the total spectral diffusion, the total characteristic spectral diffusion was about 1 gigahertz. And we've since been iterating on that internally. So what we did is once we were able to create, because it wasn't clear, right? Like when you start and you make an ensemble of these things, you make, I don't know, billions of these centers, and you're measuring all of them together. It's unclear if you can make them with high densities in an integrated photonics material. So fortunately, we were able to do so. So much so that we were able to go and identify a couple tens of thousands of them. So what we did is we patterned just pucks. And you know, it's kind of a rip on the pillars that were discussed in some of the early talks, but it's because they're not really tall. They're more like pucks than they are pillars here. And the picture is silicon. For all of its features, it actually is very good at keeping light inside. So it's a high index material, right? Higher than diamond. And so what makes it very, very good as an integrated photonics platform, like keeping all the light inside, it makes it really hard to go take a look at individual centers on a SOI structure because it actually guides the light inside the silicon. Very little of the light actually comes directly out. So what we had to do was pattern this SOI material into these pucks so that it doesn't change. We had no intention of having a high Purcell effect. In fact, we wanted exactly a Purcell of 1. We wanted to just take a look at the centers themselves, but we wanted to collect more of the light. So we got a boost in the light coupling from just moving to pucks. So we printed 30,000 of these pucks and went and took a look in a cryogenic confocal microscope and found a whole bunch of them. So here are, this is one field of them. So this is 144 qubits, basically. I think there's a little bit more than that in this that you could go and take a look at them. In fact, the we estimate there's probably about 30,000 individual qubits that we could go and talk to on that chip. And what we had is on each of the pucks, we could go and take a look at their individual luminescence. So you could go and send a laser across them and take a look at what their natural frequency is, because there is going to be some variation depending upon where the center is in the puck and how strained it is, right? But this is a pretty narrow energy range. And it's only slightly broader than what you would expect the natural energy range to be in natural silicon. If you recall one of the earlier slides, natural silicon was this big, broad, Gaussian, and then silicon-28 makes it nice and narrow. So that's kind of what we're expecting. So you can see the PLE traces where you drive it resonantly and you measure the sideband, right? So here, this is the 3 different pucks where you show these traces. And here you can see there's actually more than one T center in each of the pucks, and there's some distribution. Depending upon the puck size, there's some different number of T centers within each of those pucks. And we had our favorites. I think this one over here is called Natalie. Somebody in our group called it Natalie. Maybe that's wrong, but I like to think of it. Anyway, so we went and took a look at all of them just to go and we've taken G2s and some lifetime measurements off these. And so in this field of pucks, we had, I think, about 150 different T centers. And you can take a look at their distribution compared to their natural SOI distribution. And you can see that some of them were strained, and that TX0 and that TX1 level are mixing under that strain environment, which is to be expected, which is why it's asymmetric. And you saw the characteristic line width of this thing lines up basically with where we expect it to be. So that's nice. You could also go and see the spin. You can see the spin optically. So I think this is the reflects the title of this first observation of spins in silicon. Optical observation of spins in silicon. There's been clearly lots of electrical readout, but being able to go and take a look microscopically or optically is kind of fun. So yeah, the picture here is that this is all under the same magnetic field. So you might think that these are 3 different magnetic fields. These are actually different centers in the same magnetic field on this chip, where they have different Hall factors in the excited state. So you could actually see different optical transitions, right? So if this excited state is different for the different orientations, you can get some orientations where the B and the C transitions line up, and you get some where they don't line up. And when they line up, you only need to drive one of those optical transitions to be able to see that center, because you're never actually hyperpolarizing the spin once you've applied this magnetic field. For other centers, it's quite the opposite. The C and the B transition are a different splittings. And so if you're only driving, say, the B transition, it actually hyperpolarizes very efficiently into the other ground spin state. And that was one of our initialization and readout techniques that we use to measure the spin coherence time optically in the ensemble. So you make use of this hyperpolarization capability to initialize and even to some more complicated way read out. But yeah, so these are 3 different centers, 3 different orientations relative to a constant magnetic field. And you can see some are more split than others optically. These are 2 color scans where you can go and sweep. So here B and C are basically degenerate. So a single laser from either laser 1 or laser 2 works. Whereas here you actually need to drive B and C at the same time to be able to see number counts per second. And I'm not going to lie, these counts per second are brutal. We've since improved it from the initial by quite a bit, but this is to do with the fact that, of course, silicon does not like to spit light out, and these things don't start off natively terribly bright. It's about a microsecond luminescence lifetime, right? So that's what we were starting with. We've since improved it quite a bit, but that's where this initial publication had. Yeah, so you could go and see actually all 4 A, B, C, D transitions this way by taking a look at that 2-color map, and you can use this to initialize and read out and play all those games. So yeah, lots of spins to play with. You can probably guess where we're going. There's a lot of color center technologies out there, and I would say that we're very happy with what we have and where it's going. So although I haven't been able to talk very much about it, this work here represents the many years of work from the academic team. This is an old picture. You can tell because my hair looks completely different. I want to give a specific shout out to Mike Thewald, who of course is a silicon demigod, who's been basically one of the people who's been working on silicon since the 80s. And so one of the nice bits of work you get is there are some samples that he'd held on to since the 90s that had T centers in it. And so you could tell that actually these T centers are stable over decades, which is just wonderful. Yeah, but so a lot of this team, half of this team now is over into the company at Photonics, which I'll speak about in a second. But the more up-to-date picture is pending, but the more the accurate layout of the number, or the accurate layout of people right now on the team is right up here. We are fairly well supported, which is great because it's really exciting science and it's great to be able to move quickly. We are up on Simon Fraser academically. So sometimes you get these inversions. You can go take a look at the clouds, and I would say that they're SFU. We at SFU are hiring like crazy. Our lab is right here. So come and take a visit if flights ever permit. And the other thing I would say is which although we haven't spoken to it, the company is also scaling like crazy. We're hiring about 5 people a month. So if you're interested in this kind of stuff and want to think about the scaling and the commercialization thereof, then yeah, drop us a line. There's a lot of connections through the Whova app, and I am very interested in your questions. Thank you so much.
Thank you very much for the nice talk, Stephanie. I'm really happy that we have quantum pucks in Canada. We have a question from Claude Rohrbacher asking, can you manage to have single T centers in each puck? And if not, how problematic would that be?
Yeah, so the pucks are a stepping stone. They're not at all the scalable platform you want to do. You're going to put these things into integrated waveguides and go for it that way. In terms of the pucks, it was about on average 1 a puck for some radius pucks, and so you could go and take a look at them. But that's really the characterization tool to make sure that these things don't behave terribly badly when you put them into integrated materials, and you can go and take a look at singles. Once you're working in an integrated photonics platform, you're going to use all the other tools at your disposal. And the picture is, you know, it's silicon. It's as easy to print 1 million as it is to print 10,000, or as it is to print 4, right? So you can literally print 1 million and pick your favorite 1,000 and then carry on. So if they don't all have the exact number or the exact orientation, then you can tolerate that in a yields calculation.
Mm-hmm. I had a question about that, the integrated waveguides. Is your dipole randomly oriented, and is that a problem for that, what you envision?
It's for the same reason, right? Like if you can get it, you can target where they can locate these things, which again is not stuff that we've published, but you can get them close to where they want to be. The orientation, yeah, there's going to be these 12 different orientations. If you set it up right, you can use more than just 1 out of the 12. But yeah, there's going to be this inherent cost of doing business by working with these more complicated structures. But I'll tell you, you really do want to have those spins available. It's good to have them there locally that you can use for computational resources. So we're willing to take that price. Okay, thanks. We have a question from Rubiet El Maref, and he's asking, can you please provide us a big picture of the architecture that you're aiming for in your company? Yeah, no, sorry. That's well into NDA territory. Okay, very nice. I guess we can kind of guess a little bit, but we won't do that here. Go more into the science. Question from Philippe Saint-Jean. Since you have very homogeneous ensembles, do you observe any hints of collective excitations, for example, superradiance? Oh, yeah, we're drafting something. We're drafting something on that, but that won't be out for, my students are listening and they'll get upset with me. Probably 6 months is probably when you'll see that on the archive. It's my guess. Mm-hmm. Yeah, very nice. And it looks like we still have time for questions, but I just want to say that we're going to cut off abruptly at 3:30. So just keep that in mind if you get cut off. So the next question we have from Louis Pierre asking, oh, it's more about the company. I don't know if you can answer this. How are you managing your IP strategy through the not insignificant number of publications on or peripheral to your work? Oh, I mean, not at all. If you go and take a look at any of the major quantum outfits, they publish regularly too. You just set up a process. And fortunately, I would say SFU is like, Waterloo's up there too, but SFU and Waterloo have like fantastic IP policies, right? So they give their inventors their own IP basically. And so you can go and do a lot with it. And so that's phenomenal. But yeah, you just set up the process so that whatever patents need to go in, they go in first, and then you can write up and never block the students' progress. So it works well. Yeah, very nice. So I think we have time for one last question. But if not, we can thank Stephanie again and thank all the speakers for today for the very nice talks. It was very nice. Yeah. Thank you very much. It's a pleasure. Thank you very much for inviting me.
Oh, you're very welcome.
Thank you.